Welcome to Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Today, it's my pleasure to welcome Jen Dayon, the Senior Associate Vice Provost for Research Platforms and Shared Facilities and an Associate Professor of Material Science and Engineering at Stanford University. Jen, thank you so much for joining us today. To get us started, can you just tell us a little bit about yourself and how you got involved in nanotechnology?
Yeah, definitely. Thanks, Lisa, so much for inviting me. It's such an honor to speak to the NNI and NNCO. So I guess for starters, I grew up on the East Coast in Rhode Island, and my mom was a nurse. My dad was a construction worker. One of my favorite TV shows when I was growing up was The X-Files, and I think that was a pretty big inspiration for going into science. I loved how Fox Mulder and Dana Scully would basically solve mysteries on almost a daily basis. And that seemed like such a cool, not only career path to have in terms of solving mysteries, but to be able to work as a team. Yeah, got inspired to go into science, wound up going to college at Washington University in St. Louis, did my PhD at Caltech, which is where I was introduced to nanoscience and did my PhD in applied physics. It was just an amazing time to be in nanoscience with so many discoveries of just the uniqueness of what happens at the nanomolecular scale, and also the diversity of thought and approaches that were needed to solve, some of the bigger challenges in health and energy and sustainability. Yeah, loved kind of diving into nanoscience headfirst during my PhD, wound up doing a postdoc in chemistry at Berkeley before starting my faculty position at Stanford in 2010. Fast forward 12 years, it has just been a blast studying nanoscience and in particular nanophotonics, how to control light at the nano and molecular scale for challenges in global health and sustainability. In addition to being a principal investigator and faculty member at Stanford, like you mentioned, I also have had the opportunity to now kind of brainstorm and also oversee updates to the shared nanofabrication facilities, which has been fun to think about how different schools can come together to reimagine what the future of shared facilities will be.
What types of research projects does your lab focus on?
Yeah, great question. There are kind of two key areas that we're focusing on. In the sustainability sector, one area that we're really excited to both explore from a fundamental perspective and also enable kind of solutions for is in catalysis and chemical manufacturing. You probably know that catalysis contributes to about 35% of the GDP. So it's a huge sector of the economy. And yet so much of catalysis and chemical manufacturing relies upon fossil fuels. So generally to be able to create either pharmaceuticals or fertilizers or plastics or fibers, you need to use catalytic nanoparticles that are heated up to very high temperatures. So there's a lot of greenhouse gas emissions in the process. And what we're trying to do is develop new metallic nanoparticles that, instead of operating at high temperature, can be driven by either sunlight or solar-driven LEDs. And this not only enables more sustainable chemical manufacturing and chemical synthesis, but there's also a really exciting opportunity to increase kind of the product yield and the product selectivity. So you get more of the product that you're hoping to get in your reaction. And it's a cool area that's super interdisciplinary, from inorganic metal nanoparticle synthesis to state-of-the-art, calculations for how you can understand how different metallic atoms come together in a small nanoparticle to not only assemble, but then how the electrons respond to electromagnetic fields into particular energy distributions that can then break particular bonds. A super interdisciplinary, fun field. So that, I'd say, is one big chunk of my lab. The other is on applications to global health. We're interested in exploring sensors from essentially the small molecule level all the way to the cellular level. And one recent project that we've worked on is developing light-based methods for identifying bacterial infections and their antibiotic susceptibility. So we've had the chance to collaborate with the director of clinical microbiology at Stanford to try to develop a new platform to more quickly detect bacterial bloodstream infections. And then we've also been collaborating with a few doctors who are trying to more quickly identify the antibiotic susceptibility of tuberculosis.
How does nanotechnology play a role, if it does, in not only reducing the temperatures and the cost and the fossil fuel use that's required in processing, but also with respect to the amount of critical minerals or materials that are necessary to catalyze these reactions?
Yeah, that is a really amazing question. I'll address kind of your first question about how does nanotechnology allow us to, better understand and optimize these catalysts. And then from there, I'll address your question about how with that improved understanding, we can reduce our use on either precious minerals or expensive kind of constituent materials. So one approach that my lab has taken to understand these catalysts is using transmission electron microscopy. So we can use a focused electron beam to be able to image the catalyst with essentially atomic scale resolution. And the really cool thing about advances in electron microscopy is now we can do this imaging in kind of reactive gaseous environments. We can send in light to the transmission electron microscope. So we're really able to do these in situ measurements that allow us to see how the atoms of the catalyst are moving around and rearranging as they're exposed to a catalytic environment or a molecular environment. How illumination might be influencing what the catalysts are doing. And then we can also see how the molecules are either interacting with the catalyst or reacting off of it. So it's been a really exciting way to correlate three-dimensional catalyst structure with function. And what my lab has done is take some of the insights from transmission electron microscopy and understanding how atomic scale structure influences function, and then connect that to what we might call reactor scale performance. So then you can take your best nanoparticles that you've made, that you've observed in the TEM, have some of the optimal properties in terms of stability, in terms of like where the atoms are located, and then bring that to the reactor scale to enable very highly efficient and highly product selective catalysis. And what we've learned that kind of ties into the second part of your question, first of all, as you might expect, generally most catalysts are the most active or have kind of the most reactivity occurring at kind of the sharp corners or the low coordination number sites. So generally that's where the particle is the most reactive and where you're going to have molecules interacting with the catalyst. But the cool thing about using light to drive these catalytic reactions is that you can open up new reaction pathways that would not be possible just with temperature. As one kind of fun example of that, my lab recently showed how upon illumination, you can make almost the whole surface of the nanoparticle reactive. So now you're essentially increasing the surface area that can drive a reaction. And that's exciting because it enables you to use essentially less material. Like normally you need high loading of your nanoparticles on your support. So usually you put metal nanoparticles on an alumina support. You can kind of think about this as tiny nanoparticles decorating grains of sand, if you like. Essentially with the proper illumination, instead of having to have a lot of nanoparticles, now you can have fewer nanoparticles, but make more of the surface area active while still getting more of the product.
Can you share the makeup of your lab and the disciplines that come together to make up your research lab?
Yeah, absolutely. My home department is material science and engineering. I also have a courtesy appointment in the School of Medicine in the Department of Radiology. So I have a large number of students who are from material science, but I also have a large number of students who are from outside of material science, including electrical engineering, applied physics, chemistry, biomedical engineering. I also have a postdoc who has her PhD in evolutionary biology. I'd say that's one of the more unusual fields that has come to our lab. But when you're trying to tackle really challenging problems that are multi-scale and also multidisciplinary, that require approaches from physics, approaches from chemistry, state-of-the-art mathematics and computation, data science, and, AI. I think it's really important to have different disciplines represented because you bring kind of your own unique approach and your own lens to solving a problem. And one thing I'm really proud of in my lab too is the diversity of origins. Like there are individuals from almost every continent represented in our lab except Antarctica. And I feel like that's also brought a really unique perspective on how to solve problems, because the way that I think the global north thinks about problems is quite a bit different from the sorts of solutions that might be needed in the global south. And it's been exciting, I think, to tackle problems not only that we might experience here in California in the global north, but also think about global health and sustainability from a broader perspective.
So now that we understand a little bit about the makeup of your lab, do you have any advice that you typically provide to your students?
Probably one of my favorite pieces of advice, especially while students are navigating their life beyond college or beyond graduate school, is to think about future grandchildren that may or may not come. And when they ask you or a student what they accomplished in their life, I think it's nice to reflect a little bit upon like what you'd like to say to them, what sort of answers you'd like to have. And of course, you need to be open, I think, as a scientist to just navigating ambiguity and like unexpected adventures. Like, it's good to leave no stone unturned, because sometimes like the most esoteric, unexpected result can be the most exciting one down the road. But I think it's good to have kind of an internal compass that helps guide your decisions in life. And for me, that internal compass is thinking about when I'm 80 and, my children's children are asking me, what did you do in your life? Hopefully having the opportunity to reflect back on my career and say that I left the world in a slightly better place than how I found it.
So you mentioned your background in your time at Caltech and maybe earlier days of nanotechnology discovery. Looking back and then also looking forward, what do you think are some of the most exciting advancements that have been made over the past 20 years of the NNI? And what are you most excited about going forward?
That's a really great question. I actually just had dinner last night with a postdoc candidate, and we were talking a bit about my time at Caltech. And nanoscience was still relatively new. I remember working in what is now the Kavli Nanoscience Institute at Caltech when it was just a number of individual PIs contributing equipment like, a focus ion beam or an e-beam lithography system. It was in the basement, so completely like unrenovated. And I think the cool thing about nanoscience then is that since it was so new, it was almost like unstructured play. So it was really neat just to go in without any fear of, how you might mess up an instrument or how might things go wrong. It was just kind of like a huge playground for discovery. That's where like so many incredible ideas emerged from the sense of play. And kind of looking forward, I see almost the same sense of like discovery and play, to a certain extent in kind of hard materials like nanofabrication and characterization, but even more so in kind of soft materials and our ability now to manipulate molecules and manipulate biological matter. And I think there's a really exciting frontier on the horizon for what some are calling synthetic biology, where there isn't really the established infrastructure, so to speak, for how you create like a new synthetic biological forms, but everything from creating new proteins all the way to like 3D printed organs. I think there's a really cool future for how we can engineer biological matter moving forward. And that's not to say there aren't exciting things to be done in the hard materials. I think looking beyond silicon, there's probably a whole new like information infrastructure that can be designed by thinking about two-dimensional materials or materials like silicon carbide or diamonds. But yeah, lots of unexplored spaces in soft materials too.
Speaking of infrastructure, you have a special role at Stanford specifically focusing on infrastructure. And we spend a lot of time talking about how important that infrastructure is, not only to support new discoveries, but for student training and for also working with small companies and supporting the innovation ecosystem surrounding these sites. I'd love to hear your thoughts about the nanotechnology infrastructure.
Yeah, so I joined Stanford in 2010 when I think it was arguably among the world leaders in shared facilities, especially in nanofabrication and nanocharacterization. And when I first started is when they were installing the environmental transmission electron microscope. So in some ways, I kind of view it as my baby. I got to kind of foster it, like tinker with it. And again, there was just that sense of play. And I think I benefited not only from it being a tool that was just being installed, but from interaction with some really incredible staff scientists. In particular, Eileen Ko was an outstanding staff and turned out to be one of my closer collaborators in my early days at Stanford. I think Stanford recognized a few years ago that in order to be able to better foster state-of-the-art research and innovation, they needed to kind of rethink the model for shared facilities. Work now, I think, is so collaborative and interdisciplinary, and I think it's this convergence of disciplines where some of the best ideas are coming from. And yet shared facilities had kind of bubbled up in response to the needs of individual departments or potentially individual schools. So recognizing that to really solve problems, we need to bring communities that traditionally had been geographically separated together. And also recognizing that in many ways, shared facilities are those watering holes to bring people together. We formed something called C-Sharp. If anyone is a musician listening in, you can know where the acronym got its inspiration from, but it's the community of shared research platforms. And it brings together individuals from the schools of engineering, schools of medicine, school of earth sciences, humanities and sciences, to really think through what the future of shared facilities should be, spanning instrumentation, education and experiential learning, staffing, and then also translation. So how do we bring some of the best ideas, or at least foster those ideas to grow in the shared facilities, spanning a multitude of disciplines? How do we get students into the shared facilities as early as possible for hands-on education? How do we have students and faculty working together with the staff who really are like experts? I mean, we're so lucky to have such talented staff at Stanford who are willing to give their time to help develop new capabilities and help maintain existing capabilities. And then also, how do we allow those ideas to scale and to translate not only internal to Stanford, but like you mentioned, also with external industries and startups. So I think C-Sharp overall has been a pretty big success. I don't know many other universities that have so successfully brought together doctors and physicians and engineers and quantum physicists to kind of think collectively about what facilities should look like and how to prioritize tools. But long story short, I think what we've converged on is the need for shared space that has a certain degree of fixed infrastructure, but also a large degree of flexible space for, that kind of playing and exploration.
Jen, thank you so much for taking the time to talk with us today. I've really enjoyed our conversation. Do you have any closing thoughts you'd like to share with our listeners?
All I can say, Lisa, is thank you so much for your time, for the opportunity to speak with the listeners. It was a ton of fun. If folks have any follow-up questions or want to chat more, they're always welcome to reach out to me. They can email me at jdione@stanford.edu.